Hi, I'm Zixuan Feng. Today I'm gonna present the project, which is the comparison of different image style transfer methods. So firstly, I will explain what is the image style transfer. Then I will show you the two main methods I use in this project. Then I will make an evaluation for these two methods. At last, I will conclude what I learned in this project and make a prospect. So the first question is, what is the image style transfer? Imagine that we want to paint this picture, the dog picture, in the abstract art style. So what does it look like? The image style transfer can actually give us the answer. It's like this. So basically, image style transfer is a process of creating a picture's content with another picture's art style. In this project, we will mainly focus on two branches, the Neurostar Transfer (NST) and the image style transfer based on generative adversarial networks, which is also called GAN. In ST, the first work is proposed by Gates et al. In 2015. They used VGG19 in order to complete this style transfer mission. Then there are many optimizations based on his work, like Joseph et al. Provided to add autoencoder, and Oyanove all provide advice to use instance normalization rather than batch normalization in order to speed up the process. In the GAN part, we have many models. For example, we have cycle GAN, star GAN, TL GAN, etc. In this project, we will mainly focus on the first work provided by Gates and cycle GAN. Like I said, Gates et al. They used in their works they already used the VGG19, which is a descendant of VGG16. So that's why there is nobody who apply his algorithm on a VGG16 network. So I also wonder what the difference between VGG16 and VGG19 on performance in this image style transformation. So that's why I also evaluated VGG16 in this project. So firstly, let's talk about Neurostar Transfer. Here is a basic structure of VGG19. We can see that it's a convolutional neural network. It consists of convolutional layers, max pooling layers, fully connected layers, and softmax layers. In the training of convolutional neural network, researchers found that convolutional layers can actually extract the different features of the image. The low-level layers can extract the low-level features, for example, points, lines, color blocks. And high-level layers can actually extract the semantic information, for example, spatial information or content information. So based on this idea, Gates et al. Provided to use the VGG19 to perform the style transfer task. We use content image, style image, and output image is start with noise as inputs, and use the high-level layers to extract the content of content image, and low-level layers to extract the style information in the style image. So that's like I said, the network they use here is the VGG19, and I want to compare it with VGG16. So the difference between these two networks is here for VGG19, each of these three blocks, convolutional blocks, has 4 convolutional layers, but here for each of these three convolutional blocks only has 3 convolutional layers. So VGG19 is deeper than VGG16. Here is a second branch in my project, which is GAN. The basic structure of GAN is shown in this picture. So we can say it consists of 2 networks, one generator network and one discriminator network. So the main idea of GAN is the generator network trying to reconstruct the input image. So it's called fake image or generated image, and we mix it with the training set, which are real images, and send them to the discriminator. The discriminator network aims to distinguish the generated image from the real data. So if we apply the GAN network directly to our problem, our image style transfer problem, we will find that there is the only thing we can see about the final result is that the generated image looks like the real image, which means they have the same style. However, we cannot ensure they have this. It has the same content with the content file. So we need to add a content constraint. In order to fix this problem, researchers provided CycleGAN, which use 2 generator and 2 discriminator. So based on the basic GAN structure, we add an inverse operation on the generated image in order to compare it with the content image. So in this way, we can add a content constraint on the whole model. It's quite good, the model. However, it does need large data sets in order to train these networks, and we can see that it has 4 networks, so it's definitely time consuming. Here is the evaluation of our methods. So firstly, let's see the comparison between VGG16 and VGG19. Here is the original content image, and we can see that compared to VGG16, VGG19 has finer strokes. So in our case, in this example, it makes the dog a little bit blurred. However, it's not. It doesn't mean that VGG19 is bad. In another example, we can see that here is the original image. The VGG19 provides finer strokes, so it can paint more details. So for example, let's compare here and here. The VGG19 can draw shadows, so make it more likely to the original image. But it's not always good neither. We can see here in the pure color area, VGG19 actually add more strokes than we expected. So I call it noise. So it whether the finer strokes is good or bad, it depends on our preference. And there is another obvious difference between VGG16 and VGG19, which is since VGG19 is deeper than VGG16, so it's absolutely more time-consuming than VGG16. Another thing for methods of AST is that style file is really important for AST. So for example, we have the content image like this, and we have 3 different style files. They are both monad style. We can see that the algorithm generated 3 different results, and we can see the color tone is changed. Here is green, here is more like blue, and here is a little bit purple. So it means that if we want to preserve the color of the content image, we really need to choose a good style file. So in order to compare the AST with CycleGAN, for each original image, I chose the best result I got from my tests for AST. For CycleGAN, we can see that the quality of its generated images is more stable. It can preserve the original color. However, like I said, it's time consuming and it needs more data. For AST, we also said that its quality depends on style files. However, if we can choose the right style file, the quality of AST is quite good. It may be better than CycleGAN. So to conclude, for AST methods, the choice of style files is really important for the performance, but it does provide the possibility to get a generated image with the color tone we want. Compared to VGG16, VGG19 has finer strokes, but it's more time consuming, which is better for painting details, but it's hard to paint a large pure color area. The third point is generally CycleGAN can keep the color tone of the content image. However, if we have a proper style file, AST can give a similar result. Compared to AST, CycleGAN does need more time to train and large datasets to complete the training process, which is hard to achieve. But CycleGAN does have some special applications which is hard for AST. For example, we can replace a horse in the image with a zebra. Here is a prospect of mine. In an ideal condition, we can combine these different methods in order to union their advantages. For example, with a content file, we can firstly divide it into several parts based on different features like color tones, strokes, edges, etc. Then, according to their different features, we can choose the best style transfer method for each part. They use a discriminator like the scoring mechanism to evaluate the generated image and make changes based on its evaluation. However, like I said, it's an ideal solution, which is hardly possible in the real life for now, due to the limit of computing capability. That's all. Thank you.